All right, so today we're on topic 14, hypothesis testing. And we did talk about hypothesis testing a little bit last time around. So what we're going to do today is we are going to review that. And then we're going to go more in depth into p-values and effect sizes. P-values and effect sizes will actually come back tomorrow when we talk about power and ANOVA. But today I thought we'd do some more examples of statistical testing. We're going to introduce two new tests that are actually very similar to what we did last time with the z-test or the one-sample z-test. We're going to do two kinds of t-tests, one-sample t-test, two-sample t-tests. And then we're going to talk about type 1, type 2 errors, and these will all come together pretty nicely tomorrow when we talk about statistical power and ANOVA. So to start, this is our statistical testing process. This was the same slide that we had last week. So we set up our hypothesis first. You pick your test based on what you're doing your experiment on. You got to pick your alpha, and then only here is where you do your computation. You calculate your test statistic, you find your p-value, and then you interpret your results. So we talked about p-value kind of briefly, but here's a formal definition. A p-value is the probability of observing a test statistic at least as large as the one observed by random chance, assuming that the null hypothesis is true. So just to break down what all of that means, when you have a p-value of 0.05, usually when you're testing something with a p-value, it sort of acts like a threshold. If you remember all of the diagrams that I drew last week, a p-value kind of acts as a threshold. So probability of observing a test statistic by random chance. A p-value of 0.05 is just saying that, okay, there is a 5% chance that this observation that we're testing for just occurred by random chance, that it was just like superfluous or like spurious, and we'll get into more examples of that later, which means that there isn't actually an effect. It just so happens that our data shows that is the case. So usually if you want to be stricter with your test, you want your p-value to be lower. So a lower p-value like 0.01 will say, okay, there's a 1% chance that this has happened by random. And in our project at the end of the phase, our goal is to make sure our p-values are as low as possible so that we're not making conclusions that so happen to occur just by random chance. So this whole thing of assuming the null hypothesis is true, this definition, we will talk about this in the context of our regression later on. So don't worry about this for now. I guess we'll also talk about this with our t-test example later. Okay. So effect size. Now, effect size, we're not going to talk about too much today, but it's part of this topic's material. So just to talk about this because it's going to come back tomorrow. The effect size just measures the difference between two groups. A standardized way of talking about effect size is a statistic called Cohen's d. And what it does is it measures the difference between groups in terms of the number of standard deviations. We'll see this come back tomorrow, so don't worry about this for now, but just know that Cohen's d is measured from 0 to 1. And these are just some accepted thresholds where if it's 0.2, if the value is around 0.2, it's a small effect size, medium would be 0.5, large would be 0.8. And we'll see this in action tomorrow, actually. So let's not worry about this for now. Let's get into a t-test. So a t-test is very, very similar to the test that we were doing before. If you remember before, with our one-sample z-test, we were trying to find out whether tuition had an effect on IQs or something like that. So very, very similar. We're going to do an example of a one-sample t-test here. So here's our sample question. Acme Limited wants to improve sales performance. Past sales data indicates that the average sale was $100 per transaction. But after training the sales force, recent sales data from a sample of 25 salesmen is shown below. And then we have these 25 numbers. The difference between a z-test and a t-test is in our z-test, we had the population standard deviation. In a t-test, we do not. So if you remember before, when we talked about the IQ of the population, it had a mean of 100 and a standard deviation of 16, I think is what I said. But in this case, we're only given the mean of 100. And actually, a t-test is a lot more common in practice versus a z-test because a lot of times you don't have that population standard deviation. So chances are, if you're asked to do some sort of statistical testing to see if something had an effect on something else, more likely than not, it's a t-test. And when in doubt, actually, if you use a t-test, you're actually being much stricter. Okay, so here we have our question set up. Let's go into our statistical testing process. So first we set up our hypotheses. So the hypotheses here, we have our null hypothesis saying that there is no effect on this sales training. So here we just want to see whether the sales performance has actually improved or not through this training, through this sales training. So started at $100, all we want to see is there a significant amount of increase in sales performance? So our null hypothesis, which means no effect, is that the mean is at 100. Our alternate hypothesis, or our alternate hypothesis, is that the mean is greater than 100, that the mean has increased. And then let's just set our alpha at 0.05 because that's the standard. So numbers to note and calculate, we have our population mean, which is 100. The number of people in our sample is 25. The mean and standard deviation of our sample being the sample over here. This is just calculated using like NumPy. 109.54 as the sample mean and a sample standard deviation of 13.3. And the degrees of freedom, which is something we'll talk about in a little bit, degrees of freedom is always n-1. And so n-1 here, 25 minus 1 will give us 24. So these are numbers to note. Cool. There's a lot going on here, but let's take a look at all these different things. So remember how with our z-test, we calculated some sort of z-score? You can actually do something very similar with t-test. And instead of calculating a z-score, we want to calculate a t-statistic. So here we're going to calculate this t-statistic, which is 3.57. And then with this graph, you can calculate that. Another way of looking at this is, hold on, let's see here. Another way of looking at this is we have to compare our values. So what we're going to do is we're going to put up the t table, where is my t table? Okay. So we're going to pull up our t table to find our critical t table, critical value of t. Okay, so what do we have here? We're actually doing a one sample t-test that is one-tailed. So the way that we read the t table is we need to know several things. One, the degrees of freedom, which is red on the side here. And then also the alpha and whether it's a one-tailed or a two-tailed test. And then from there, you just read out your number that you can compare your t-statistic to. So first, we know that we're doing a one-tailed test because this is looking to see whether our mean has increased or not. If the question asks about whether the mean has changed and doesn't indicate whether it goes up or down, it becomes a two-tailed test. So in this case, it's just a one-tailed test. So here we go one-tail, and then we want to look at our 0.05 value. So this is how you read it, one-tail 0.05, okay. Let's look down for 24 degrees of freedom. So for 24 degrees of freedom, our value that we have is 1.711. So that's how we can make our conclusion. 1.711 is here. And what this means is that this shaded area over here is 0.05. So this is 0.05. Our t-statistic that we calculated here using this formula, which I will show you in a bit, is actually done automatically for you using SciPy. This t-statistic is 3.57. And 3.57 on this standard t curve is all the way over here, greater than 1.711. So if you sort of remember when we were drawing diagrams the last time, ideally you want your t-statistics to be higher or your z-score to be higher to reject your null hypothesis. So because our t-statistic falls outside the region of our critical t-value, we can safely reject the null hypothesis. Alternatively, because we talked about p-value earlier, we can also calculate the p-value associated with this t-statistic. And the p-value associated with the t-statistic here would actually be, and let me bring up my drawing over here, would actually be the area under the curve to the right here, which as you can see is going to be very, very small and less than 0.05. Because if this area is 0.05, this area is definitely smaller than 0.05. So the probability of that just occurring by chance is very, very low. And so that gives us more confidence that this training has had an effect on the sales force. Any questions about this? Okay, so it's a very, very similar testing procedure as what we did last week. So this is a one sample t-test. And remember that the difference here is that we did not have our population standard deviation. Instead, we just had a different way of calculating our statistic and two different ways of making a conclusion. One, by comparing our statistic. Two, by comparing our p-value.
A quick question.
Mm-hmm.
So for t-tests, I know they don't use population standard deviation, but they do use sample.
That's correct.
Okay.
You're usually given the sample. So like in this situation, they gave you the sample, like the actual sample values. But if not, they will at least give you the sample mean and standard deviation if they don't give you this entire array of values.
Okay. All right. Thank you.
You're welcome. Okay. Anything else? All right, so the next thing we're going to talk about is a two-sample t-test that is slightly different. And here I'll talk about the difference between a one-sample and a two-sample test. So a two-sample t-test is really just used to compare two groups. Rather than comparing one small group to a population, you're just comparing the differences between two groups. And this is a pretty common example. So an example here, let's use this one. So let's see, I can't read right now, but okay. In the context of controlled experiments, you'll often see talk about the control group and the experimental or treatment group. So imagine you're trying to test the effectiveness of a drug. A group will get like a placebo drug that doesn't actually do anything, and a group will get the actual drug and they want to test whether there is an effect. So in a drug test example, the control group is given the placebo and the treatment group is given the actual drug. So researchers will be interested in the average difference. And in this case, we're talking about blood pressure levels. You're interested in the average difference in blood pressure levels between the treatment and control group. If there is a statistically significant enough difference, then yes, the drug is effective, but if not, the drug is not effective enough. So this is a setup. 50 subjects in the control group have an average systolic blood pressure of 1 to 1.38, who have been given a placebo drug. And then 50 subjects in the treatment group have an average systolic blood pressure of 111.56 after treatment with the drug being tested. So the apparent difference between experimental and control groups is negative 9.82. So you see how like this difference in the two numbers are 9.82. But with 50 subjects in each group, how confident can a researcher be that this measured difference is real and not by chance? That is not that it so happens to be that we have this group of subjects that just happens to already have lower blood pressure. Therefore, you might falsely claim that this drug is effective. Does that make sense? The fact that yes, there is a difference, but we want to see how statistically significant is this difference. And so when you want to do a comparison like this, you want to do a two-sample t-test. For data science, we won't really be dealing with these kinds of differences. However, a very, very common use case of two-sample t-test, which we'll actually talk about next week, is in A/B testing, like testing the effectiveness of different things. Like for example, one very common thing is if you're doing a marketing campaign and you have two different versions of this campaign, you give one version to one group of people, another version to another group of people, you want to see which one is more effective. You can do a 2-sample t-test, and actually next week we'll walk through that example. So let's run through this example first. Let's figure out whether this measured apparent difference of negative 9.82 is statistically significant or not. And we're going to actually go through the exact same hypothesis testing steps. And they're all on this page, so let's take a look. So first, this is our hypothesis. There are multiple ways to notate this. So in this case, I'm just saying that, okay, mean 1 minus mean 2 equals to 0. And that just means that there is no difference in the means of our groups. Our alternate hypothesis is that mean 1 minus mean 2 is not equal to 0, saying that there is a significant difference between our groups. There are other ways that you can write this. This is the standard way of writing it, I will say. However, you might also see it as mean 1 equal to mean 2 as a null hypothesis, and then mean 1 not equal to mean 2 as an alternate hypothesis. So you might see it this way. It's the same, but I believe that this is the standard way of writing it. Okay, so that's step 1. We've chosen our test. Our test is going to be a 2-sample t-test. Next, we're just going to go with our regular alpha of 0.05. And as you can see here, in the setup of the question, we just care about the average difference in the blood pressure levels. This is actually one of, like, if you're taking a statistics test and they have the word difference versus, greater than or lesser than, it's actually a key identifier that they want you to do a 2-tilt test. There is a chance that this drug was just not formulated the right way and actually increased blood pressure. And so in order to account for that difference when you're doing a statistical test, it's good to know that this is a 2-tilt test. So because we're using a not equal sign, here we're going to talk about 2-tilt test. And this is the first 2-tilt test that we're doing so far. And the idea of a 2-tilt test, and we'll actually see from the t table in a little bit, is even though alpha is 0.05, that 0.05 is actually going to be split up across 2 sides of the t curve. So what that means is, here we have our diagram here that we've seen before. And then this area down here and this area down here are each 0.025. So they add up to 5%, if that makes sense. You're just splitting your alpha across the 2 sides. Okay, so these are some numbers to note and calculate for a 2-sample t-test. This formula is a little bit intense, and I'll show you all that there is a 1-line code that you can do to do it all, but just for the sake of going through the motions and going through the process of this, you need to know the means of both and also the number of subjects in each group. And then I don't think it's important to know these formulas. It really isn't, but you need to figure out your statistic from here. So I put on another slide how you can this is how you calculate the t-statistic using this formula over here, where you have the means of each. So this will be 1, 2, 1, this is 1, 1, 1. The n1 and n2 each are 50 down here, and then s squared is calculated by this formula here. So it's pretty complicated. This is not important at all, but this gives you the conclusion that the 2-sample t-statistic here is negative 1.891. We just want to see whether with an alpha of 0.05, where does this negative 1.891 stand? Cool. All right. So let's take a look at our t table here. So in this t table, we have an alpha of 0.05, and on each side we have 0.25. So we're actually going to look at this example over here. A 2-tilt test of 0.05, which is in this column here. In terms of degrees of freedom, something that's very interesting is you can sort of see here that the degrees of freedom after 30 increments by a lot. So yes, our number of people per sample per group is 50. And yes, we take 50 minus 1 to be 49. Technically, our degrees of freedom should be 49. But as the number gets bigger, if you remember from last week, we talked about how as the number of observations increases, it starts to look more and more like a normal distribution. That's why the incremental numbers don't matter as much. But we can also sort of conclude that, okay, the number is going to fall between 40 and 60 here. So the number that we should be looking at is going to be around 2. So that's where our threshold is going to be at a critical t value of 2. Okay, so looking at that, our critical t value of 2, actually this dotted line over here shows us that it's 2. Now, where does negative 1.8 stand in comparison to that? So now that we know that our critical values are at 2, our negative 1.8 is over around here. If you see that line over there, is roughly around there. So with our last examples, we wanted our t-statistic to be as far out as possible. But in this case, it actually fell within the boundaries. So therefore, this effect of negative 9.81 was basically not big enough to be statistically significant. Yes, it did miss it by a little bit, but we set these alpha values to have strict thresholds. So based on this, we actually cannot reject the null hypothesis. So even though there was a difference of negative 9.82 between the two groups' blood pressure, we actually cannot conclude here that the drug was effective. So if this t-statistic happened to be a little bit less than, if it happened to be just an absolute value of 2 or more, then sure, the drug becomes effective. But in this case, because this t-statistic was a 1.8, it was not great enough. The difference was not great enough. Any questions or thoughts about this? Okay.
So if it falls within
these dotted lines.
Yes, if it falls within these dotted lines, does that conclude that they can't conclude that the drug was effective?
Exactly. And if you want to even connect it to p-values, here the p-value of this would probably be a little bit greater than 0.0. It will probably be greater than 0.025. And 0.025 is the threshold here because we're splitting it across the negative side and the positive side. But back to like your point that you're making, yes, because the statistic itself, the t-statistic fell within the critical region, we cannot conclude that the drug was effective.
Okay. All right. Thank you.
You're welcome. I want to go quickly to the next slide because I'll just show you here that, the conclusion is you fail to reject the null hypothesis that the drug does not make a difference in blood pressure levels. So within stats models, which is a library that you'll see in your labs, you can do this automatically. So this is another way to do it, which is a one-liner using stats models, which is another library that we're going to talk about. Experimental and control are each a list of numbers. And with these two lists of numbers, in this one line, it tells you what your t-statistic is. And even better, it tells you what your p-value is. And you can see here that the p-value is 0.06, which is saying that there's a 6% chance that the observed difference was completely by random. So therefore, it's saying that sure, yes, there was a difference of 9 in the blood pressure levels, but that difference was not significant enough because there's still a 6% chance that that could have occurred by random. Usually you want to look for p-values that are as low as possible such that, the observed differences are less random, are less due to random chance. So honestly, this is more important, but it is good to understand the whole process of setting up hypothesis tests. But as a data scientist, what you will be doing is really just this one line here. And it's up to you to interpret what these values are. And this also exists for z-tests as well, and all of the tests that we're going to talk about going forward. All right, any questions before we move on to the next thing? Okay. Next, we're going to talk about type 1 and type 2 errors, kind of related to p-values. So in statistical testing, everything is based on a probability or statistical significance. So there are inevitably going to be situations where we reject the null hypothesis when we shouldn't have, and vice versa. And so these situations are known as type 1 errors and type 2 errors. So if you reject the null hypothesis when you shouldn't have, it gives you a type 1 error. And if you do not reject the null hypothesis when you should have, that's a type 2 error. In statistics, basically the probability of having a type 1 error is equivalent to your alpha, because with the alpha set at 0.05, there is a 5% chance that what you observe is correct by random, right? So that's just saying that there's still a 5% chance that you're making a conclusion that isn't true. Going back to that sales example, we did conclude that yes, the sales training did have an effect, but that t-statistic is associated with some p-value, which is the probability of it just being by random chance. So therefore, there is that probability of getting a type 1 error. Okay, so a type 1 error, the probability of a type 1 error is basically equivalent to your alpha. And a type 1 error is usually a false positive because you are saying that something has an effect when it actually didn't. That's type 1 error. Type 2 errors are a little bit more complicated, and we'll see why. And we'll also talk about type 2 errors in more context tomorrow. So a type 2 error is failing to reject the null hypothesis when it is actually false, which is false negatives. So the probability of a type 2 error is actually called beta, but beta is also something that you have to calculate depending on what effect that you are, what effect you're observing. So for example, in our last case here, when we saw a measured difference of negative 9.82, it also depends on that value that you're observing. And we'll actually get into more of designing these tests and experiments tomorrow. So don't worry about this for now. But just know that beta is the probability of a type 2 error, which is, we're going to go through that calculation either tomorrow or next week. But associated with that, you have a power of a test, which is 1 minus beta. I have one thing that I want to show you all over. Let me see, where is it? Okay, let me pull it up real quick. Where it shows you how alpha and the power of the test are related. Let me pull it up, sorry about that. Usually I have it embedded in the slides. Here it is, okay. Okay, so we'll actually go through this in more detail tomorrow. But basically, you can see here, we can play around with alpha. And if we play around with alpha, it basically affects the power of your test. If we play around with sample size, it also can affect many different things. And if we change our significance level, and if we also decide to change our effect size, it also affects the power of your test. So all of these things will come in hand, but we'll talk about that more tomorrow. Okay, what I want you all to get away from here is whether you have a type 1 and type 2 error, it is kind of a trade-off. It is usually a trade-off between type 1 and type 2 error. If you want to reduce the number of false positives, you are most of the time giving more allowance for false negatives. It's very hard to design an experiment or a test where you can perfectly, make predictions and conclusions. So therefore, there's usually some sort of trade-off between type 1 and type 2 error. That's what I want you all to take away from today. And then also whether you prefer type 1 or type 2 error really does depend on context. So as an example, I can talk about some capstone projects that I've seen recently. So for example, the last capstone project I saw was predicting whether Bitcoin will go up or down within a day, and using some data, predict whether Bitcoin will go up and down for the day. And for every day, you're going to make a prediction of whether it goes up or down. So if it goes up, let's say that's a positive. If it goes down, that's a negative. So in that scenario, if we're thinking about our false positive and false negatives, there's a difference between saying the price will go up when it doesn't versus saying the price will go down when it actually goes up. Depending on the context, you might like one over the other. For example, if you are investing in Bitcoin and you're using this project to help you choose whether you want to invest or not, it's a lot better if the price goes up when you expected it to go down versus when the price goes down when you expected it to go up. So again, really depending on the context, you might prefer type 1 or type 2 error. And something I'll have you all do when you get to doing your projects is to think about whether in your context, type 1 error is more important to get rid of, or type 2 error. Cool. Any questions or thoughts about that? Okay. So again, I want to highlight that in our homeroom, I have this doc over here that talks about that basically is a summary of what is important to take away from the stats section of this phase. And so by today, we pretty much talked about most of these things. So I really recommend maybe after you're going through material to go through these questions a little bit and maybe make a copy of this doc and see if you can answer those questions for yourself, especially after you're going through material. I think, yeah, pretty much all of these over here, we should know by now. But going back to our slides, this is the last slide. So any questions to end off for today? I understand that today's session had a lot of loose ends that we haven't really talked about yet, but tomorrow and the session after that is when all of it will come together, I promise.
So type 1 and type 2 errors, they occur in 1 and 2 sample t-tests.
That's right. Yeah. The context in which they appear, yeah, it depends on the context. So in this example, a type 1 error is saying that the drug actually worked when it didn't, and a type 2 error is saying that the drug didn't work when it really did. And similar in this example with the Salesforce, a type 1 error is saying that the training helped when it didn't. Type 2 error is saying that the training didn't help when it really did.
Okay.
And you're welcome. And usually in the context, depending on what values you decide to go with or are given, you can actually find out the probability of making a type 1 and type 2 error given your experiment. Cool. Anything else?
So just for type 1 and type 2, so usually it's type 1 is sort of the equal to the measure of the alpha.
That's correct.
And type 2 is the measure of the beta.
Yes, it's a measure of beta, but we haven't talked about how we calculate beta.
Okay. All right.
Yeah, we'll talk about beta more tomorrow, and also in context of a coding problem on next Tuesday.
All right. Thank you.
You're welcome. Cool. Any other questions? Awesome. So the main things that we talked about today is conducting 1 sample and 2 sample t-tests. We also talked about the definition of a p-value, which is actually very, very important. And then also we started talking about type 1 and type 2 errors, that of which we will get more into tomorrow. Cool. If there are no other questions, Going once, going twice. Have a good rest of your night, everybody. Any questions you have, please let me know. I understand that this material is extremely abstract, especially for those of you who haven't seen a lot of stats before. As long as you can answer those concept questions, I'm confident that you'll be able to do whatever data scientists need to do. Also check out that playlist of videos that I sent out to your channel. That's honestly a really, really good resource. And yeah, as usual, just Slack me if you need anything. All right, well, if there's nothing else, I will see you all back here tomorrow and also at your one-on-ones.
Thank you.
All right,
Thank
have a good
you.
evening, everybody.
Bye.
Have a great evening. Thank you.
Good night.